Welcome to our October meeting. Um, I'm very pleased to have our speaker for this month will be Emily Levesque, and she'll be our feature presenter. Then we will go on to our business meeting, public observing committee report, outreach report, finance report. Did I mention in the news with Steve Rand? So we'll have that also. Uh, a bird that mimicked a black hole, the astronomer that discovered microwave ovens, a telescope that can fly. The science of astronomy is filled with true stories and tall tales of the adventures and misadventures that accompany our exploration of the universe. Join Dr. Emily Levesque, author of the critically acclaimed popular science book, The Last Stargazers, to take a behind-the-scenes tour of life as a professional astronomer. We'll learn about some of the most powerful telescopes in the world, meet the people who run them, and explore the crucial role of human curiosity in the past, present, and future of scientific discovery. Emily, without further ado, I will unshare my screen and let you share and take it away.
I will. Let me go ahead and share mine. And thank you all again so much for inviting me to join the meeting this month. And I'm so excited to get the chance to talk to all of you. I'm originally from Southern Massachusetts, so it's great to be virtually back in New England. And I'm happy to talk tonight a bit about The Last Stargazers, my book, and the stories of what life as a professional astronomer is actually like. I wrote this book because I wanted to give readers and give curious people a window into what these very unusual jobs are like. And I fell in love with astronomy and went into it thinking I would get to spend a lot of time studying space. The adventures of the field wound up being a really unexpected treat. And when I was getting ready to write this book, I remember going to a big conference of writers. It was my first time writing a book for a popular audience. This conference was wonderful. I got the chance to participate in a panel where fellow authors were talking about, great first lines of books, and these first lines that are iconic and just set the scene for bringing readers into another world. So you remember, Call Me Ishmael from Moby Dick, or It Was a Dark and Stormy Night from A Wrinkle in Time. And we started talking about our first lines, and it got me thinking, well, okay, I've written this book about professional astronomy and what it is like to do this very strange and unusual job and all these adventures we have going all over our planet to study the rest of the universe. How does my book open? How do I welcome people to this idea? And I realized the first line of my book is, have you tried turning it off and on again? So it does not sound like a sweeping space adventure. It sounds like every horrible phone call you've ever had with your internet service provider. This question, though, is actually the most terrifying thing that was ever said to me at a telescope, because I was asked this while sitting here. I was a graduate student observing at the Subaru telescope at Mauna Kea Observatory in Hawaii. I had one precious night on this telescope to get crucial observations for my PhD thesis. The night had been going great. The sky looked something like this. Everything was clear. Everything was beautiful. And everything had been going fine until one of the computers in the room made this awful little bloop sound. And I looked across the room. I looked at the only other person on the mountain with me, who was the telescope operator. She looked back at me, and I think trying to reassure me, she said, oh, don't worry. I think it's fine. I think the mirror is still on the telescope. And I don't think this was as reassuring as she had hoped, because I didn't know the mirrors could come off, telescopes this big. And she then proceeded to explain to me what had happened. To give you some clarity, by the way, when I say a telescope this big, this is a picture of me standing beneath one of the other telescopes that it's a similar size to Subaru. Subaru has an 8.2 meter primary mirror from end to end. This is me standing under an 8.1 meter mirror. You can see me at the bottom of the screen. You can see the scale of the mirror we're talking about. The mirror that the operator had been talking about that could apparently come off the telescope was actually the secondary mirror of Subaru. If you look at a large telescope in a dome like this, what you usually have, and this is a picture of Palomar as an example, is the big primary mirror, so that 8.2-meter mirror near the bottom of the screen, and the little secondary up near the top. In Subaru's case, that secondary mirror was still about 400 pounds and about 2.5 meters across. And what had happened was the mechanized supports holding that mirror in place had apparently failed. That was what the blunk had been telling us. We happened to have the telescope pointed fairly straight up, but this blunk was warning us that without proper support, if we tilted the telescope too far to one side or the other, that secondary mirror would fall off the telescope and go plunging about 70 feet to the concrete floor of the telescope dome if we were lucky. If we were unlucky, it would be hitting that massive primary on the way down. So we put in a phone call to the day crew at Subaru asking, what do we do? How should we deal with this? Are we really about to break the largest piece of glass in the world? And they very calmly said, no, you're probably fine. It's probably a false alarm. There's probably nothing wrong. They kept saying probably over and over. It's probably just an error. You can probably fix it by turning the telescope off and on again. And it seemed really impolite to say, this is a telescope. This isn't my home modem. I'm not comfortable with power cycling as a way to fix the telescope. But we hung up with them, and the telescope operator looked at me because this was ultimately my call. And all I could think during that whole phone call was just of stories spinning through my head of other telescopes that had met really untimely ends, who'd had horrible things happen to them. The one that I kept thinking of the most was this one. So this is the Green Bank Radio Telescope in West Virginia, or rather, this was the Green Bank Radio Telescope in West Virginia. It was at the time a 300-foot radio telescope, one of the most powerful telescopes on the planet during its heyday. It made incredible early radio astronomy observations until one evening when, in the midst of observations, it went from this to this. It horribly collapsed in the middle of an observing night. The story became infamous in the field. All of us had seen this picture. I couldn't remember what had caused it to fail. I was fairly certain someone had tried turning it off and on again at the time. So I was now stuck on the mountain trying to decide what to do. Because if they were right and it was a false alarm, I should really turn the telescope off and on again and keep observing. Otherwise, I would be giving up a really important night of observations for my PhD thesis for no reason. I could delay my graduation by months, even years, if I gave up this night of observations. On the other hand, if they were wrong and this alarm was real, I would become the grad student that broke Subaru. So I had to sit there faced with this question of turning it off and on again and deciding what this would do to my observations, my job, and my career. And this is how I've decided to open my book, The Last Stargazers, because it's a glimpse into the behind the scenes world of professional astronomy and the observations that we take. I'm sure you're all very aware that everybody loves the pictures we all take of space. They love the beautiful pinwheels that you get in a galaxy or these filaments of a nebula. The sort of romance and beauty of space has pretty universal appeal. But what not very many people know are the stories behind where our pictures come from and how working in professional astronomy actually works. I think when most people picture an astronomer, they picture something like this. If you Google picture of an astronomer, these are the stock photos that come up. And it's usually a man. He has a beard for some reason and is wearing a lab coat for space safety. And he's standing next to a little telescope that he's looking through with his eye. And I actually don't think this is a bad depiction when you think about how most of us interact with astronomy. Most people come to astronomy through astronomy club open house nights, through an observatory open house on a university campus, through a neighbor with a telescope in their backyard that invites people over to look and enjoy the view. And they sort of imagine their interactions with astronomy just made big. They don't necessarily know about the accoutrement of taking really professional astrophotography or what it's like to actually have to travel to a telescope in the middle of nowhere. So the love of astronomy is there, but the picture of astronomy is a little bit skewed and a little bit limited. I was absolutely in this boat when I was growing up. So this is me at age 6, and I'm very proudly sporting my Hubble Space Telescope t-shirt because Hubble had launched that year. My brother describes my face in this photo as, what do you mean 6-year-olds can't use Hubble? I already knew then that I wanted to do astronomy, that I wanted to study space, but I really didn't know much about what astronomers actually did. I mainly came to astronomy through amateur astronomy. My dad had this fabulous 8-inch Celestron that we would pull out and set up in our backyard in Massachusetts periodically. I would help him sort through eyepieces and try to point the telescope at the Orion Nebula or Saturn. And I knew this was really fun. I just figured my job one day as a grown-up would be more of that. I finally got my view of what real professional astronomy was like when I got to college. Until then, I just sort of figured that I would be a professional scientist like the ones I'd seen in the movies from when I was growing up. If you look at a movie like, Twister or Jurassic Park, you grow up thinking that most of the time your science is going to be chasing you. I adored the movie and the book Contact as a kid, but even I realized that you probably didn't discover aliens every day. So in college, I sort of had this big question mark about what professional astronomical work would be like. The summer after my sophomore year, I was a student at MIT. I traveled to Southern Arizona with a now longtime colleague of mine, Philip Massey, to observe for 5 nights at Kitt Peak National Observatory. We showed up there, we dropped our things off in the dormitory, and we wandered into the observatory dining room. We sat down at a table. Phil knew everyone at the table, and he said, "Everyone, this is Emily. She's a new student of mine, and this is her first night at a professional telescope." And they all said, "Oh, no, great, that's fine, that's fun, that's awesome." And they said, "Remember to order your lunch now so that you can bring it up to the telescope with you, but don't eat it too early. You'll get hungry, but wait to eat it until about midnight, 1 a.m. It'll help you stay awake." And then someone else said, "Keep an eye on the floor here. We have scorpions in this part of Arizona." We actually had a woman who had a scorpion crawl up the inside of her pant leg and sting her in the middle of an observation. And then someone else said, "Oh, that's nothing. I know a guy that had a raccoon crawl into his lap in the middle of observing in a dark dome one night, and he just pet it until it went to sleep." And then someone else said, "Well, I know a guy who was in a dome when it got struck by lightning." And they just started passing these like wild sea story adventures of astronomy back and forth. And I was sitting there listening to them with my fork frozen on the way to my mouth. I couldn't decide whether I wanted to sit there and just listen to them storytell all night, or whether I wanted to run off to the telescope and see about getting some of those stories for myself. And I realized in retrospect that this was how they were inviting me to the field. And this was how they were sort of welcoming me and giving me a preview of what this job was going to be like and some of the wacky quirks of it that I had coming my way. This night and this storytelling came back to me years later when I was writing my book, The Last Stargazers, which does use these stories to give people a behind the scenes tour through the adventures and lives of professional astronomers, and also looks at how much astronomy has been changing over the years. It was chosen as an Amazon Best Book of 2020. It's been a finalist for several big science writing prizes. It came out in the midst of the summer of 2020, which is possibly the worst time in recorded history to release a book. But it's been really great to see the enthusiasm and response that it's gotten. And the act of both sharing the book with people and writing the book were both unbelievably enjoyable. To actually do my research, I traveled to observatories all over the world. I got the chance to visit places like the Gravitational Wave Observatory here in Washington State. I got the chance to fly on a telescope, which I'll mention more in a little bit. I really got a chance to enjoy a lot of different details of professional astronomy. But my favorite thing that I got to do for the book is actually shown in this picture on the lower right. It looks boring, but that is my trusty voice recorder. I recorded interviews with 110 of my fellow astronomers. I talked to everyone from people who had been observing in the field for 60 years to brand new grad students who had just been on their first observing run. I wanted to hear everybody's stories about their memorable nights at observatories, what they loved most and what they remembered most about observing at telescopes, and how they felt about the field. So I'm not a trained investigative journalist. I'm a professional astronomer. So I mostly just turned on the recorder and let people talk and let people tell me stories. But I did want to have some structure to the interviews and some structure to the book. I didn't want the book to just be a goofy collection of anecdotes. So there were 3 questions that I asked everyone to help shape what the book is about. And I'll be talking about those 3 questions to structure this talk. So the first question that I really enjoyed asking people was, what is your most memorable second or third or 10th hand observing story? Everybody told me their own stories of being at a telescope, but I was trying to get at the stories that get passed around the field, the stories that people were telling that night at dinner with the "I know a guy that so-and-so," something that may or may not be true. I wanted to track down the sort of big legends of the field and see if I could suss out the real story and get it written down for posterity in the book. When I asked this question, there were a couple answers that came up over and over. I think the most common one was some version of, there were these weird radio bursts that happened. They were somewhere in New Zealand, and people thought it was astronomy, but it wound up being something funny on the ground. What were those? And people would sort of half remember the details. I wound up hunting down and getting to the heart of the story, and it's one of my favorite types of story in astronomy. So these weird radio bursts that everyone was talking about were originally detected at Parkes Observatory in Australia. Parkes in 2007 detected this brief, weird blast of radio emission that it couldn't identify. It did not fit with any previous observations. It didn't fit with predictions of any recent phenomena or any recent studies of, we think something in the sky should give us a brief flash of radio waves. It should look like this. It really caught people by surprise. It happened. And then the observatory just sort of moved on. It was marked as something strange and left as a mystery. Years later, in 2012, a young woman named Emily Petroff showed up at Parkes for graduate school and said, I'd like to do my PhD thesis on these weird bursts of radio emission. When she told them that, the immediate response was, oh, no, don't bother. We've actually been detecting these all the time. We think the telescope is probably just picking up something weird on the ground. We're getting radio interference from a source on Earth rather than something interesting in astronomy. They had actually given these bursts a name. They nicknamed them perytons. So these are mythical creatures that look like one thing, look like one type of creature, but cast the shadow of something else. Emily wasn't convinced. She thought there might be some real astronomy buried in all that data. But in order to do that, she had to first prove what they were actually detecting. She had to try and separate out the weird ground detections from the real signals coming from space. So she wound up working with the entire staff of Parkes. When she ultimately published a paper on this, the authors actually included the secretarial staff, the janitorial staff, everyone who worked at Parkes, because everybody was part of figuring out this mystery. And they really started searching through everything they could to explain these bursts. And their first clue came when they realized that as the telescope was coming in and detecting perytons, the perytons were clustering around the lunchtime hour. So space is weird. Nothing in space cares what time lunchtime is in Australia. So this was the immediate first clue as to what might be going wrong. This is an aerial picture of Parkes Observatory, and you can see the three buildings pointed to with arrows that are administrative buildings. They have offices, desks, they have break rooms where people can head in and make themselves a cup of tea, or maybe microwave some lunch. So all of these buildings had microwaves in them, and they homed in on the microwaves as possible explanations for what could be causing these perytons. If you read the paper, they are so wonderfully thorough. They are consummate scientists about this. Some poor person read through the entire manual of a 1970s microwave to explain exactly how it worked, exactly what sort of frequency it should produce if it was working well, exactly what could go wrong. They ran through the observatory and carefully microwaved high and low power versions of microwaving a ceramic mug full of water. They tried different durations of microwaving. And when they did this, they would always check the telescope. And no matter what they did, microwaving things carefully, they never produced a peryton. The microwaves did not seem to be a serious source of interference. And finally, someone noticed that they were really doing this experiment like careful scientists. They were not doing it like hungry people microwaving their lunch, because when you microwave popcorn or leftovers or something that you're about to eat, we all do it. We get impatient and we watch the microwave count down and we go 3, 2, good enough. And you open the microwave a little early. Yes, you do. And that opening stops the microwave, stops the cycle, and then you can get your food. When they tried this, when they ran the microwaves, but then stopped them by opening the door rather than waiting for the cycle to finish, they did it. The telescope produced wound up detecting a peryton. And they went back and they said, all of these strange detections were just impatient people on site or in the nearby area microwaving something and opening the door too early. We have explained these weird bursts of radio light. They are definitely coming from the ground. We can delete all of these signals from our database of interesting objects, except for one. That original signal from 2007, as it turns out, could actually not be explained by microwave interference. That was actually a real event. And today there is an entire subfield of astronomy dedicated to studying fast radio bursts. We have massive catalogs of fast radio bursts. We're still not entirely sure where they're coming from, but we're starting to narrow down the sorts of phenomena, usually distant dying stars, that could be producing them. All of this was made possible because Emily Petroff and the staff at Parkes had to back up and discover microwave ovens in their data before they could move forward with the actual science. So people loved telling me this story or telling me different versions of these stories, where a telescope accidentally detects something that is interfering with our ability to study the universe from right here on Earth. I actually learned a great story shortly after I published the book. It was too late to include it, but it included another radio telescope. This is Green Bank Observatory in West Virginia, which I showed a picture of before. I showed you that picture of the tragically collapsed radio telescope. And this is its beautiful replacement. They were able to rebuild a newer, bigger, better telescope on that same site. They rebuilt at that site for a very particular reason, because this part of West Virginia is a national radio quiet zone. It's an entire area that is designated to be as radio quiet as possible, with very minimal interference from any radio sources in the surrounding region. If you're very close to the observatory site, microwaves are kept in special protective cages so that they don't produce any errant signal. They don't have cell phones. There is no Wi-Fi. The vehicles on the site actually use diesel engines because the little sparks of a spark plug in an internal combustion engine are enough to create little blasts of radio light. So they do everything to keep this area pristine and as quiet as possible. It's also, as you can see, a really pristine natural area. And living in that forest surrounding Green Bank Observatory is a population of little flying squirrels that some biologists not too long ago decided they wanted to study. They wanted to study the squirrels, study their movement, study their population characteristics. And they did this by catching a bunch of squirrels and fitting them with little radio collars. So they then unleashed an adorable swarm of radio interference sources around this telescope. And to hear the staff tell it, they basically couldn't do anything for weeks. They would go to try and observe, a black hole at the center of a distant galaxy, and nope, they're just getting squirrels. They're trying to do some radar observations, and nope, squirrels. They basically had to do engineering work and wait for the batteries in the little collars to die. So tiny squirrels could in fact take down one of the world's biggest radio telescopes. These sort of spurious or fake detections sound like they would be limited to the radio, where we can get lots of radio signals from the ground, or maybe even optical light, where you could get an accidental flash from headlights or a struck match that could be mistaken for a flare, a bright flare by a telescope. But we actually even get these when you look at gravitational wave observatories. So this is an aerial picture of the LIGO Gravitational Wave Observatory here in Washington State. And these observatories, I think, are some of the most engineeringly marvelous things that we've ever produced on the planet. I think they are on par with the moon landing. If you look at these observatories and how they're built, they consist of two perfectly straight arms that are exactly the same length. Each arm is 4 kilometers. The central building between the two arms that you see has an incredibly complicated central room that boils down to firing a laser down each arm and then back to measure the length of the arm. And when you think about what gravitational waves are, this makes sense. Gravitational waves are ripples in the fabric of space-time. They're basically compression waves, where they would sort of squeeze and then stretch space-time as they propagate through it. They're a consequence of general relativity, and they come from really gravitationally violent incidents like black holes colliding. If a gravitational wave were to pass through Earth and the space-time that Earth is in, it would slightly squeeze and stretch our planet and everything on it just a little bit. And that's how an observatory like this would detect a gravitational wave. I described that laser in the central building. If everything at this observatory is normal and there is no gravitational wave passing by, that laser will get fired down to the ends of the arms. It will bounce off the ends of the arms and arrive back at that central building at exactly the same time. The arms are exactly 4 kilometers. There is no gravitational wave. Space-time is behaving as we would expect. Now, if a gravitational wave were to pass by, the arms would be squeezed and stretched because they're at a perfect right angle to one another. Inevitably, the gravitational wave would slightly compress or stretch one arm, but not the other. And because of that, when the laser is fired, it now has a slightly different travel time depending on which arm it's going down. The laser beams arrive back at the central building at slightly different times, and this is seen as a signal. We've detected, we think, a gravitational wave. We've actually had this understanding of gravitational waves for decades and known exactly how to detect them. And the thing I always tell people is that LIGO has been detecting gravitational wave since it was first built in the early 2000s. The problem is it also detects everything else, because any tiny thing that affects the travel time of those lasers or the perfect precision of measuring the length of those arms could mess with your signal. These observatories frequently get stymied by massive earthquakes, even on the other side of the planet. This observatory detects trucks driving on the highway that you can't even see in this picture because it's so far away. They only let visitors come to the observatory on Tuesday mornings because that is when it's closed down for engineering, because the footsteps of visitors are enough to disturb it. Rain hitting the ground is enough to cause interference. Most of the job of a gravitational wave observatory is filtering out all these sources of noise. And for the most part, they can do it very reliably. There are occasionally, though, sources of noise that trick them. And my favorite one that LIGO told me about at our site in Washington came from these very suspicious marks that appeared on the cooling piping on the exterior of the observatory in the middle of a hot summer day. The tubes are kept in a perfect vacuum. The temperature is kept quite cold. They have cooling tubes running to the actual pipes of the observatory itself. And in the middle of summer, the condensation on the outside of them will freeze. They were starting to get strange signals in the data, and they were starting to notice these weird little peck or hash marks on the outside of the ice. They finally realized that these marks and the strange signals were related, and that there was a nearby raven that they quickly nicknamed Thirsty that had decided pecking at this ice was the best way to get a drink on a hot day. They very carefully filed a operations report about this. They identified the peck marks. They went out and they checked that they were the right size as a raven beak. They dispatched a grad student to pretend to be a raven and go out and tap on the things to see if they could reproduce the signal, but they successfully did. They were able to later eliminate this as a potential source of noise, but they did get a kick out of pecks from a thirsty bird managing to mimic the same signal that you would get from colliding black holes at this observatory. So people loved telling me these we detected something strange and had to search through our data to explain it stories. I think the reason a lot of astronomers like these is because we are studying very fantastical things. We're studying colliding black holes that squeeze space-time. We're studying dying stars in other galaxies. They sound ridiculous and they sound absurd. And I think people appreciate the care that astronomers take to separate the truly absurd, these strange phenomena on the other end of the cosmos, from the everyday absurd, a bird pecking at your instrument or a microwave oven being opened too early. Knowing that astronomers can do this and that we can be skeptical of our own data is an important part of the job. It's something that a lot of astronomers take a lot of pride in, knowing that when we turn our attention to the real science, we're being as careful as possible. So people loved telling me stories like this, and I loved including as many of them as I could in the book. The second question that I asked a lot of my colleagues were what they thought would surprise people the most about our jobs. I explained to them that this book was being written for a popular audience, that a lot of astronomy enthusiasts would read it, but that people who really didn't know a whole lot of astronomy might find the book in their hands. And I asked them, what do you think would be the biggest disconnect between what people think professional astronomers do and what we actually do? The most common answer was we don't look through eyepieces, because most large professional telescopes, like the Subaru telescope that I was at, don't even have eyepieces anymore. We go straight to digital detectors. So a lot of people would say, we don't look through an eyepiece. But then they would go on and say, our job is actually even cooler than that. As fun as it is to stargaze, and as much fun as we all still have doing it, even as professionals, we really get to have some incredible adventures as part of our job. And people loved telling me their, wildest adventure story from their time in the field. And I got a wonderful collection of all these different tales and all of these different pictures that I could use to really illustrate just how diverse and how interesting the field of astronomy could be. This, I think, was my favorite story that I got to hear from people and that I eventually got to experience myself. So this telescope is until recently it was actively operating. This is NASA's Stratospheric Observatory for Infrared Astronomy, or SOFIA. It is an infrared telescope built into the back of a specially modified Boeing 747 that is able to fly up into the stratosphere at about 45,000 feet, so higher than commercial aircraft fly. Once it's up there, it then opens a special door in the back of the plane to expose the telescope to the pristine sky that's now above most of our atmosphere's water vapor, so that it can detect infrared light that would normally never make it to the ground. This is the latest in a succession of airborne astronomy missions. And I was very lucky to get the chance to actually fly on board SOFIA for my own research as part of my work on this book. I got the chance to go down to Christchurch, New Zealand, where they were flying and observing the Southern Hemisphere sky. We actually flew so close to the Antarctic Circle that we were able to see the Southern Lights from out the windows of the plane, which is the first time I'd ever seen the aurora. And that was the coolest possible way to check that thing off my bucket list. It was an unbelievable adventure. And I couldn't believe that my job had actually brought me to an experimental aircraft over Antarctica, flying through the Southern Lights just to observe some stars and just to do some of my research. So it was an amazing story that I loved including in the book. Airborne astronomy actually sometimes takes a lot of other forms too. I talked to colleagues who launch instruments on research balloons or on suborbital rockets, trying to get sort of as close to space as possible without the expense of launching a full-on space telescope like Hubble or like Webb. I also talked to people who really traveled to extensive parts of the planet to get to the best astronomy they possibly could. I think the example that we're all most familiar with is traveling to places to study eclipses. I had a colleague at the University of Hawaii when I was there as a graduate student who had pioneered much of the field of professional eclipse chasing, of bringing research grade equipment to, in this picture, Svalbard in Norway, or to a remote island in the Pacific to chase totality at a solar eclipse and really get crucial research observations of the corona. So the stories she had for me of some of the incredible places that they wound up traveling were just fascinating. I am not following her example and traveling down to Oregon from here for tomorrow's annular eclipse, but we are going to get it at about 80% here in Seattle. And even a partial solar eclipse is so fascinating. I've been lucky enough to see one total eclipse that is written about in my book. I know that in New Hampshire, it'll be at around 10, 15%. And even that, even seeing that little bite taken out of the sun is fascinating. So talking to somebody who had pioneered professional observations and professional eclipse chasing was completely fascinating. And I loved the chance to include it in the book. I also talked to colleagues who had traveled to places like the South Pole and the South Pole Millimeter Wavelength Telescope. They described working at the South Pole during sort of the daylight half of the year, and they described wintering over at the very remote research station near to the literal South Pole itself rather than the edge of Antarctica. Their stories of coping with such a long stretch of night, even for an astronomer who should love it, were completely fascinating, and it really started to marry the idea of astronomy and research as an area where you can still sometimes undertake full-on expeditions. They were fascinating stories. I also in the book include the story of this man on the lower right. And I just got through talking about how astronomers are not men in lab coats standing next to little telescopes. He appears to be completely breaking that promise, but this man actually gets an excuse. So this is George Carruthers. He is the patent holder as the inventor of ultraviolet astronomy. He invented the ultraviolet camera. And he is standing next to this little 4-inch telescope that he designed and built for a very specific purpose. This telescope was actually brought to the surface of the moon as part of Apollo 16. John Young and Charlie Duke, the two astronauts who were on the moon with it, operated it for the full duration of their mission. And they were able to get some of the very first ultraviolet astronomy observations ever. They got to look at our own Earth, some young stars in the Milky Way that were very ultraviolet bright. It really served as a benchmark for starting the field of ultraviolet astronomy. And the same technology that went into that telescope is now in places like the Hubble Space Telescope and other UV telescopes that we operate largely from space. So people really loved telling me all these different adventure stories of the places they got to travel for their job. They also had some sort of wacky stories about adventures that would come to them, even if they were doing astronomy research relatively close to home. One of the most infamous stories, especially here in the Pacific Northwest, came from a former colleague at the University of Washington, Doug Geisler. So this story took place at Monastash Ridge Observatory, which is a small but fantastic observatory here in central Washington state. Right now, it's a place where our undergraduate researchers train. In Doug Geisler's day, back in the 1980s, it was a research telescope for graduate students doing oftentimes stars-related work for their PhD thesis. Doug was observing at Monastash Ridge Observatory for the very first night of his PhD thesis observations. At the time, he was taking notes the way everybody else did at observatories at the time. He was meticulously filling out the telescope's night log. And you can see a glimpse of his night log here and all the details that he carefully kept track of. The date, May 18th, 1980, which might be familiar to a couple of people, And he carefully notes, I observed for 10 hours. I observed from 10 p.m. to 4 a.m. for a total of 6 hours. Hours lost, 0. The sky condition was excellent. He basically had the beautiful, perfect beginner's luck of an excellent first night at a telescope. Doug finished his observations on the night of May 18th, and then he went to bed early that morning. He woke up, he remembered waking up vaguely later that morning and thinking that he'd heard sort of a faint rumbling or a sort of weird distant sound and going, oh, that's weird, falling right back asleep. He then woke up at noon, and every astronomer has had the experience of falling asleep after a long night of using a telescope and then waking up sort of squinting at the daytime sun. And he was ready for that. He opened the door of the dormitory, ready to walk into a sunny day, ready to start another beautiful day of observing. When he opened the door into utter blackness. He couldn't see a thing. He grabbed a flashlight, and the beam just immediately got swallowed by the air. There was this awful sort of sour brimstone smell going on around him. He thought he was living through nuclear fallout or the end of the world, and he was completely alone. He was the only person on the mountain. So he went running back indoors. He found a radio. He started frantically searching for a radio station, and he finally picked up a report explaining that earlier that morning, Mount St. Helens had erupted. Now, the eruption of Mount St. Helens was an incredibly dramatic eruption that basically blew the side off of the mountain. If you look at satellite footage of the eruption, you can see what happened to Manassas Ridge Observatory, because when Mount St. Helens erupted, you can see where the volcano is, you can see the volcanic plume, you can see where Doug was, and you can see what he was standing in when he opened the door of the observatory. He was fortunately physically safe, but he was in the midst of this massive volcanic fallout. He very sensibly realized what was going on, knew that volcanic ash was corrosive, and ran out to the telescope to carefully cover the mirror so it wouldn't get damaged by the falling ash. He was then able to eventually wait out the worst of the fallout and carefully drive home. And while he was waiting, he made a absolutely legendary entry in the night log. Hours lost, 6. Reason, volcano. Sky condition, black and smelly. Comment, I am the last survivor of the war. So this log entry is still up at Manassas Ridge Observatory. This story is still told to especially our students who now learn on the telescope, pretty much telling them, you can do all the planning you want. You can be very ready for a perfectly clear night, but you can never take a night at the telescope for granted. You can never be quite certain what's going to go wrong or what adventure is going to suddenly befall you while you're on the mountain. So the last question that I asked my colleagues was how astronomy had changed since they began observing. I know that astronomy even now is undergoing very rapid changes in how we do our observations, how we operate telescopes, what kinds of telescopes are running, and how that then in turn colors the scientific questions that we ask and the scientific questions that we answer. I got the fortune to talk to some colleagues who had really had decades and decades of experience in astronomy. I talked to lots of folks who had, until quite recently, used glass photographic plates to take their observations. And this was what they immediately pointed out to me. They would say, at the start of my career, I observed with glass plates. I would get a box of glass sheets from a company like Kodak that were chemically treated to darken when exposed to light. I would take these plates into a dark room, turn off all the lights. I would cut the plate down to a size that would fit in the telescope camera. I would climb into the telescope and I would spend all night carefully swapping plates in and out and exposing them one by one before going into a dark room at the end of the night and developing them. This was what I had to do in order to get my observations. I had colleagues who would pull plates out of their desk or out of a file cabinet and show them to me. And I think to the students that I talk to now who have only ever known digital imaging, this sounds like a goofy or primitive way of doing observations. They have only known iPhones and digital cameras. But you can see in this example just how exquisite the observations are. This is a photographic plate of NGC 6946, which is one of my favorite galaxies. It's this beautiful spiral galaxy that's hosted 11 core collapse supernovae in the past 100 years. It's by far the record holder for the most supernovae hosted by a single galaxy. In this photographic plate, you can pick out these spiral arms. You can see hints of the dust in the galaxy. You can see knots of high star formation or bright points where you can see where the young stars are distributed in the galaxy. I have a student working on their PhD thesis on this galaxy right now. So the photographic plate is beautiful. But every single astronomer who told me stories of using photographic plates then went on to say, oh, I have fond memories, very cold memories, but fond memories of using these plates. I don't miss it because digital imaging is so incredible and the kinds of science we're able to do is so stunning. So you can compare the photographic plate picture of NGC 6946 to the exact same galaxy, but observed with the digital cameras of Subaru, the telescope that I was at the very beginning of this talk. And the difference is just night and day. You can see how completely spectacular that image is and how much incredible detail we can get at in this galaxy. My student who is doing our research is actually focusing on individual clusters of young stars in this galaxy and studying exactly how old they are, exactly how these clusters may have formed, really getting at the history of how the most massive stars in this galaxy are forming, because that could prove to be the key to explaining why this galaxy has hosted so many supernovae. So lots of people called out the technology. Many of them also wound up pointing out that because of these technological changes, our job as astronomers, our job as professional stargazers is really starting to change. One of the coolest research trips that I got to take for this book was actually going down to the Vera C. Rubin Observatory in Chile. Now, at the time I went, it was under construction. It is still under construction, but it is very nearly done. I keep getting exciting pictures from colleagues about every final step being put together. This telescope has a simple but really beautiful job. It is going to be surveying the southern sky, taking basically a picture of the entire southern sky every few nights for 10 years. It is going to be giving us a decade-long movie of the night sky. And for any of us who study variable stars or who look for a new bright supernova in M101 or a nearby galaxy, we know how exciting that is because there are so many little changes in the night sky that the Rubin Observatory is going to detect. The telescope is huge. It has an 8.4-meter primary mirror. It's going to be able to do this to an unprecedented depth and just give us piles and piles of potential variable stars or potential supernovae that we can follow up and study. Nobody is going to be going to Rubin Observatory to observe. I won't be submitting a proposal and going and sitting there for a night telling the observatory what to do. It's going to be following its preset program. When I use data from Rubin, I will be looking at an online database and saying, that supernova sounds cool, or that star sounds interesting. And I will either be just downloading the data to work at from the comfort of my desk, or maybe seeking out another telescope that can take follow-up observations. It's very different than the type of astronomy we've done up until now. It's amazingly powerful. Like I said, we're going to have huge databases available to us, and those databases will be available to anyone. Anybody who has access to Rubin's data can download what they need and take the observations. They don't have to have a university or a grant that can send them to Chile. The catch, though, is that Rubin is only going to find some strange objects. It'll maybe point out, hey, this star is variable or this star is weird. We will still need follow-up observations to really find the truly odd things in its data set. And I always like comparing this to the very oddest type of star that I've ever studied and that I've ever had the chance to observe. This star is something known as a Thorne-Zhitkov object. So these are very strange stars that we think form when a red supergiant and a neutron star in a binary system wind up merging. So that neutron star, this sort of leftover dead husk of a massive star that is supported by principles of quantum physics instead of, the nuclear fusion that supports a star like our sun, gets swallowed by a red supergiant, a star that looks from the outside exactly like Betelgeuse. The neutron star spirals into the center of the star. It eventually disrupts and even replaces the star's core. And what you wind up with is a star that has a neutron star heart, a quantum physics supported heart. The trick is that from the outside, they still look just like Betelgeuse. That neutron star is so tiny and its effects are so subtle that you could easily, at a glance with something like Rubin, mistake this for just a normal red supergiant. My colleagues and I actually had been studying red supergiants. Anna Zhitkov of Kip Thorne and Anna Zhitkov emailed us and said, have you ever searched any of your objects to see if they could be Thorne-Zhitkov objects, TZOs? And we said, no, this sounds very cool. We'll have to design a very careful research program to see if we can figure out how TZOs would look. We don't get much hint from how they form, but we can sort of back up and imagine the formation process to tell us how these stars should appear. The way that a TZO forms is that you start with two hot, massive stars in a binary. These two stars are orbiting one another, and eventually the more massive star in that binary will collapse and die as a spectacular supernova, leaving behind a neutron star. That neutron star then gets swallowed as the companion expands to become a red supergiant. And what you wind up with is this cold star, but with that neutron star buried at the center, doing very strange things to the star's interior. It can produce a very odd chemical signature that you would not expect in a normal red supergiant. You would get excesses of weird elements like molybdenum or rubidium or lithium that you would not otherwise expect to see. We decided to build an entire observing program around taking really detailed spectroscopy. So taking star's light, sorting it out according to its color, and then searching for little signals of rubidium or molybdenum to see if we could see excesses. We got 2 nights of time at Las Campanas Observatory in Chile on very classical telescopes, the Magellan telescopes with 6.5-meter mirrors that we actually flew to and sat at and directed, pointing to red supergiants one by one, saying, check that one, check that one, check that one. I think we honestly thought that we wouldn't find a Thorne-Jitgov object on this search. We thought maybe we would establish a baseline. We'd have a nice publication saying, here's how much molybdenum a normal red supergiant has, because it wasn't something that had been previously studied. We would maybe say, this is what a normal supergiant looks like. Here's what a very molybdenum enhanced one might look like. We'll keep looking. Now, as we were sitting at the telescope, we were watching our data coming in. And another thing that a room full of astronomers always understands is that our data did not come in looking like this. I think people imagine red supergiants. When I talk to reporters, they ask me for pictures of my research, and they think I'm going to give them this, just these beautiful, glistening, perfectly processed, perfectly colored red dots just sparkling away in a star field. And not only does the data not come in this processed, we were taking spectroscopy and just taking light and stripping it out according to color. So our data looked like this. It looks like a bad signal on a TV. Now, when we got the data from our Thorne-Jitgov object, which is what I have on the screen, we were sitting at Magellan with one of our collaborators, Nydia Morel. She was an expert at observing with these telescopes and with the specific spectroscopic instrument we were using. So she was able to look at this image. I've zoomed in on the interesting part. She looked at this on a much bigger, busier screen, and she immediately identified these weird little bright spots in the data. And she saw those and immediately said, I don't know what that is, but I know that I like it. Now, those spots are not signs of molybdenum or rubidium or lithium. What they are spots of glowing hydrogen atoms. Those are emission lines from hydrogen atoms in this star's outer atmosphere. What we later realized was that Thorne-Jitgov objects are expected to pulsate a little bit. Those pulses can actually excite hydrogen atoms that wind up glowing and giving us these little bright patches in the star spectrum that we'd never seen in another red supergiant. So with these observations, we were able to look back, measure the molybdenum and rubidium and lithium, realize we were seeing strange chemical abundances, and then say, we have discovered the first candidate for a Thorne-Jitgov object. Kip Thorne and Anna Jitgov had predicted these stars back in the 1970s, but nobody had ever seen signs of one until our observations. I loved this as an observing run because it was such a classical puzzle. We put together what we were looking for. We made an observing plan. We applied for time. We flew down to Chile. We actually added the star that ultimately wound up being our candidate at the last minute, sitting at the telescope and scribbling through our list. They're observations that could have only been made by doing this very classical type of astronomy. The Rubin Observatory on its own won't be able to take observations like this. It won't be able to target a single object, and it won't be able to pull out that kind of detail. You need this sort of classical follow-up in order to do it. What Rubin will be able to do is detect heaps more objects like it. It could detect, for example, those pulsations that wind up exciting the hydrogen atoms and give us a list of strange red supergiants that we could then chase for follow-up. A lot of people talked to me about how it felt like the classical era of astronomy was starting to disappear, or that Rubin Observatory and others like it, or some of our space telescopes, were really changing the sort of romance and the adventure of going to a telescope and following up something strange. But a lot of people then amended that with, it's great that we're having these new telescopes built. We just need to keep them all. We need to have enough funding and enough support to build something like Rubin, but keep alive an observatory like Sophia, which sadly had to close last year due to lack of funds. It got its budget cut. In an ideal world, we would have the funding for Rubin and for Webb, this astonishing new space telescope that we have operating. But we'd also be able to keep running airborne observatories, rebuild or keep working on beautiful radio telescopes like the one in West Virginia. We would really ideally have all of these resources working together and the resources available for anybody who wants to do professional astronomy or participate in astronomy research to keep going. So that was the takeaway that I ultimately wound up putting in my book, that our field is changing very rapidly. We're seeing a lot of shifts in how astronomy is done and who does astronomy, but we don't actually want to be the last stargazers. We want to keep stargazing and the research on it as alive and supported as possible as the field keeps evolving. So on that note, I will leave my book information up on the screen. I also did want to mention, for folks who are interested, I have a course that was recently released through Wondrium or the Great Courses, if anyone's familiar with it, that tells more stories like this. It talks about the great heroes and great discoveries of astronomy. So again, putting human faces in human stories on some of our biggest discoveries. So that's available now via streaming or via DVD. And then the book is obviously available to buy too. And I'm here to answer any questions you might have. Thank you very much.
Thank you, Emily. I am so awed by this and so amazed. I learned so much. So great presentation. I open up the floor to everybody. Feel free to unmute and ask Emily your question.
I have a question. How is AI changing the scope of research in astronomy?
This is a fantastic question. It's changing the scope in amazing and wonderful ways. The University of Washington, where I'm at right now, is actually one of the founding partners of Rubin Observatory. And we specifically have an eScience Institute and a data-intensive research and astronomy organization that focuses on how we're going to be dealing with huge volumes of data in astronomy. I want to make sure I get this number right because it's absurd. Rubin is going to produce something like 40 petabytes of data a month. And that's obviously much more that we can process no matter how many grad students or astronomers we throw at it. So machine learning and the ability to apply big data techniques to astronomy is massive. We're also starting to work on ways to train an AI to do something like automatically give a star a spectral type or classify a star based on its color. I have students who are working on this and finding really interesting results on how you can classify a star with brightness, color, and how it varies. Interestingly enough, my husband actually works on explainable AI. And that's a really cool key point in astronomy because we don't just want the AI to spit out a magical answer. We want to explain how it got to that answer and pull physics out of it. So it's a really exciting tool for astronomy right now.
I would say the limits of AI is that it only will maybe explain what already is known, and you're trying to look for the unknown.
You know, a lot of times people are trying to look for the known in funny ways. We can say something like, we know exactly what a red supergiant looks like. How many red supergiants are there in that galaxy? And how many blue supergiants are there? And what does that tell us about the evolution of the galaxy? So looking for known things is a surprisingly common part of astronomy, and getting the AI on that is great because that's what the AI can do. Like you said, it can't ask a weird question. It can't think of an unknown for us to explore, but you want the scientists working on that. And you want our time freed up from the things that an AI could do.
Very good. Any other questions for Emily?
I don't have a question. I read the book. It's a wonderful book. My favorite part of the book is where she steps out in off of one of the sites down in Chile and just looks at the southern hemisphere and sees the stars as they are. It's a wonderful description. It's a great book. I really appreciate it.
Thank you.
Emily, just a wonderful talk. I plan on getting the book. I love the way the human experience dovetails right in with the scientific method, and that wonderful presentation. Thank you.
Thank you. One of the things that I had in mind when I wrote the book, and I was writing this prior to 2020, but it's really easy to forget that science is done by people, and a lot of human curiosity and a lot of human quirks wind up coloring the way we do our research. So it was fun to put that into the book. And it sort of sneaks the science in. I got the chance to talk to some folks who told me they really weren't into science books and they really weren't terribly into astronomy, and they weren't sure they would like the book. But then when they read it, they were pulled in by the human side of the stories, and they realized along the way that they had learned science almost inadvertently. Because to understand why an astronomer is staying up all night, why you're having lunch at 3 a.m., why you're, blasting music in the dome to stay awake, you have to understand why we make those decisions for the research. So it was a fun way to combine those two elements.
Emily, in terms of the misconceptions of scientists, anything in the school system, anything in public education, for example, any stories about that in terms of such outreach?
In terms of misconceptions, that wasn't something that came up a whole lot. It's funny, I mentioned this in the book. I didn't ask any of my colleagues how they became astronomers. I was looking for stories once they were astronomers. I wasn't looking for the origin stories. Everyone told me anyway. Everybody said, well, I first got interested in astronomy because of so-and-so. And a lot of people called out enthusiastic teachers, or their school took a trip to a planetarium and they'd grown up in the middle of a city and this was the first time they'd seen stars. I think that just based on what I've seen, a misconception that I would love to see dismantled is I think we still look at math as scary and hard, and we still look at science and nowadays more and more programming as this intimidating, scary thing. I talk to students who deeply love astronomy but are petrified of programming. And especially now with just really like what you see is what you get type interfaces, they're frightened the very first time they look at a command line. And they think I'm going to push something and break the whole computer, which is possible, but it's probably not something they're going to do. And I would love to see that dismantled in public schools, because there's a lot of love for teaching science and teaching math, and you can't do it without the math and the computer science. You can't do it without the language. We've been running into this right now with our very young son, that a lot of people are talking about, oh, we'd love to teach our very little child a second language or have them learn multiple languages, which is amazing. But I would love to see more people recognize, Python is a language, Fortran is a language, learning AI is a language, or learning math. It's all connected in the same way. So I would love to see that supported more, because it would help support science literacy and a love for how we do science.
Very good. Any other questions for Emily Levesque? Emily, thank you very much. This was captivating, and I enjoyed this immensely.
Thank you so much.
We are lucky. And Emily, have a good one, and we will go to our business meeting. Thank you very much.
Sounds good. I'll be signing off, but thank you again so much, everyone, for inviting me. This was immensely fun. I always love talking to astronomy societies, and hopefully sometime I'll be back east and I can come to a meeting in person.
All right.
Thank you.
Bye.
Bye.